first things first, definition of Laplace transforms. Essentially, Laplace transform is a transform where you actually have to move from the time domain to what they call the frequency domain, right? You have a function that is in terms of a real variable, in terms of time variable, and then you have to use what they call a Laplace transform to convert it to a complex variable s, right? That's why you see everywhere s, and once you invert the transform those time variables, you have things in terms of s. Okay, essentially they are used to convert things from very highly complex forms or mathematical expressions to something that is more simplistic. You may have some things in terms of exponential or differential form, and then once you do the Laplace transform, actually this is the mathematical expression for Laplace transforms. Right? You have a f of t function defined for all real numbers for t greater than 0, right? Because if or equal to 0 actually, and then essentially you plug it into this equation and integrate from infinity. This is infinity. Between the bounds of infinity and 0, you integrate the f of t times e to the negative st. Okay, so whatever the f of t is given, if they tell you f of t is 5t or f of t is t squared, right, or f of t is 1, an impulse, right, you always want to, if you want to do the manual longhand calculation, for instance, you may need that if you don't have this what they give you in the exam in tables, right? Then you have to use the first principles to actually calculate the Laplace transform. And what it ends up doing is that because when you find the integral of exponential functions and you apply boundaries to it, you end up getting things that are more simplistic algebraic expressions, right? So that's kind of the reason or the point of all this transformation to a frequency domain. Because in that frequency domain, you're going to have algebraic expressions that are easy to solve. And once you finish you get your solution, you now revert back to time domain, right? And that's when you now need to apply your inverse Laplace transforms. Okay, so the parameter s is a complex number frequency parameter, right? The unit of that is per second, right? Because frequency is per second, right? So the unit of s is actually per second. It actually can have a real part to it, and it can have an imaginary part, right? And when you want to plot different poles or zeros on an s-plane, it's important to know if you're plotting or your s equals to something is a real number, or it's an imaginary number, or it's a combination of, it's a complex number, right? So that you can know what plane, what part of the s-plane does it lie, and all that stuff. Okay. So here in the page 39, there are tables, Laplace transform tables that show conversion from time domain to frequency domain, and then they also show a couple of inverse Laplace transforms, right, from the complex frequency domain to the time domain. All right. Now they only present the basic ones, right? They do show, I think, 2 cases where you actually combine 2 of the principles, but then they, of course, expect in the exam they're going to give you things where you have to build up on that. You have to apply more than just one Laplace transform to get the other one, right? And then that's when you start going into the principle of convolution and all that stuff. Okay. So during the course of the class or in the exam, they may refer to Laplace transforms with this notation, right? They may just say L of L, which is the Laplace. F may be represented by F or F of t, okay? And you would rarely see F there. So either they use this, or this, right? F of S or all these two, okay? So just kind of get conversant with the notation.